In this video, we're going to look at some word problems that require the law of sines or cosines to solve. In our first example, a pilot is flying over a straight highway and determines that the angle of depression to two mileposts that are 5 miles apart to be 32 degrees and 48 degrees, respectively. We want to find the distance from the plane to each of the two mileposts and the elevation of the plane. As with any kind of problems that deal with triangles, it's often a good idea to start by drawing a picture of all of the given information and then using that to determine how we want to proceed to solve the problem. So in the scenario that we're given, we have these two mileposts that are 5 miles apart, and I'm just going to label them A and B. And this here, of course, is the ground, so there will be 5 miles there along that straight highway. And we have a plane up in the sky, somewhere between, so I'll just represent that with this dot. And the plane is following some horizontal track in the sky. And we're told the angle of depression from the plane down to each of the markers. And so if we draw, say, the line of sight here from the plane down to mile marker A, this angle right here is our angle of depression, so this angle here would be 32 degrees. Remember that the angle of depression is made with the horizontal line of sight of the plane. Similarly, if we connect up the plane line of sight with mile marker B, we get an angle of depression of 48 degrees, which would be this angle here, again with the horizontal. And this is the total of the given information that we have. But however, from this, we can actually determine all three angles of our triangle. For example, we know that this angle here in our triangle is going to have to add with 32 and 48 to give 180 degrees. And since 32 and 48 degrees add to 80 degrees, this angle here must be 100 degrees. We also know that this angle down here at A, between the ground and that sort of line of sight up to the plane, would be 32 degrees. The two angles here, this angle and the angle of depression at the top, are alternate interior angles from the parallel lines between the ground and the flight of the plane. Likewise, the angle over here at B will be 48 degrees because that angle and the angle of depression from the line of sight down to mile marker B will be alternate interior angles and therefore are both the same. We'd like to find the distances A and B. Notice I'm going to use the convention that the lowercase letter is the side opposite the angle. So here, lowercase a is actually the distance to mile marker B, and lowercase b is actually the distance to mile marker A. Now that we have everything labeled, notice that we do know an angle and its opposite side. We know the 100-degree angle at the top of our triangle, and we know the 5 miles at the bottom. This tells us that the law of sines will likely be the useful tool in order to find the values of A and B. So to find side length A, we're going to take the sine of 100 degrees and divide it by the side opposite that, which is 5. And that should equal the sine of angle A, which would be 32 degrees, divided by side length A. We can use this to solve for side length A. It's going to be the 5 times sine of 32 degrees, divided by the sine of 100 degrees. And this will approximately be 2.69 miles. We know the units in miles because that is the unit for the number 5 in the first denominator. So just a note here that this is actually the distance to milepost B, even though it is represented by side length A. To find the distance to milepost A, we want to find the value of lowercase b, and we'll follow kind of a very similar procedure. The sine of 100 degrees over 5 will equal the sine of 48 degrees all over b. I use cross multiplication here to solve for b. It's going to be 5 times the sine of 48 degrees divided by the sine of 100 degrees. And using a calculator, this would be approximately 3.77 miles. And this will be, of course, the distance to A. So this gives us two of the three quantities that we're looking for in this problem. The third quantity is the elevation of the plane. And in order to find that, we're going to use one of these two values that we just found, either A or B, along with the standard right triangle trigonometry. Here again is our picture of our situation. And notice that I went ahead and put in the two values that we already have found. The distance from the plane to milepost A is 3.77 miles, and the distance from the plane to milepost B is 2.69 miles. We now want to find the elevation of the plane, which is the height above the ground of this particular plane, which is represented by the length of this green side here from the plane down to the ground, which is perpendicular to the ground. Right? Notice that we actually then have two right triangles. For example, we have the right triangle formed by angle A, the height of the plane, and the side of length 3.77. Notice that since this is a right triangle, we do have an angle and a side length, and we would like to find the elevation, which maybe I'll call H, and so we have two of these three values, and we'd like to find the third, and so we can use the standard right triangle trig ratio here. Notice the height is our opposite side of angle 32 degrees, and the 3.77 is the hypotenuse. And so here we can use the sine function, which gives us the ratio of the opposite to hypotenuse sides of the right triangle, and the sine of 32 degrees to find the value of H. So specifically, the sine of 32 degrees is going to be H divided by 3.77. We can multiply this by 3.77, so H will be 3.77 times the sine of 32 degrees. And our elevation is going to be approximately 2 miles. Notice that we could have also used the other right triangle, which would have had the hypotenuse of 2.69 miles and an angle of 48 degrees. If you try that on your own, you should see you also obtain almost exactly 2 miles. In this example, we have a car that's traveling along a straight road for 1 hour heading east, and then turns 35 degrees onto another road for 30 minutes. If the car has maintained a constant speed of 40 miles per hour throughout the trip, we'd like to determine how far it is from its starting point. Again, the first thing that we should do is to sketch a picture of our scenario, and this should tell us how we will go about solving this particular problem. Okay. So we start with our car heading east, so we'll draw a horizontal line. So we'll start here at A and end at B. And then the car makes a 35-degree turn. And so the way that turns are going to be measured is by looking at the direction that our car is initially going. And then if it turns, let's say it turns to the left, 35 degrees, this angle here will be 35 degrees. The angle from the initial line of sight, the original direction the car was traveling, to the new line of sight or the direction of travel of the car. And then the car will reach its position here at C. And we'd like to know the distance it is from its starting point, so we'd like to know this value here, which of course is side length B, opposite angle B. Now, we're not directly given any information about the triangle, angles, or sides, but we are given enough information to figure out some of these pieces. So, for example, the angle here in the triangle is going to be 145 degrees because we need these two angles to add together to give 180 degrees, which is the straight line. So 180 minus 35 is 145. We also know two of the side lengths. The side from A to B, we know took 1 hour to travel and was traveling constant 40 miles per hour. So this side will be 40 miles long. And we know the side from B to C was traveled for 30 minutes for half an hour at 40 miles per hour. And so this would be 20 miles long. And so now we have two side lengths of our triangle, and we have our angle between them, and we'd like to find one other side of that triangle, the third side, and this is a natural law of cosines situation. So here we have that b squared is going to equal 20 squared plus 40 squared minus 2 times 20 times 40 times the cosine of 145 degrees. We can substitute all of this into a calculator, and we see that b squared is approximately 3,310.64. And by taking the square root of this value, we do get that b is approximately 57.54 miles. So our car here is approximately 57.5 miles away from its starting point.